Hi, my name is dr. Ahmath. In this video lecture, we are going to solve the final exam on Linear Algebra 2020. The exam contains three parts. The first part contains 10 short answer questions. Where we're going to solve the problems essentially on the vector operations and the simple matrix operations. The second part contains the 5 true-false questions. And the last part contains the two problems, one on the SVD decomposition and another on the QR decomposition and the least square problem. So let's start from the first problem of the first section where we need to do the simple vector operation. So we need to multiply these two vectors as a scalar product. Let's first of all evaluate these two vectors. It's going to be 2u minus 3v. This is going to be 2 minus 2, 4 minus 4 minus 3 times the v, it's going to be 3, 0, 6 minus 3. And if we subtract these two vectors, we obtain minus 1, minus 2, minus 2, and minus 1. So now we're going to add the v to the 2u. That's going to be 2 minus 2, 4 minus 4, plus the v itself. It's going to be 1, 0, 2, minus 1. And if we add, what we get is 3 minus 2, 6, and minus 5. So essentially, when we multiply these two vectors as a scalar product, we need to multiply them component-wise. So essentially, the first component to the first, the second to the second, the third to the third, and the last to the last, and then we have to add them. So this is going to be minus 1 times the 3, plus minus 2 times the minus 2, plus minus 2 times the 6, plus minus 1 times the minus 5. So if we open up the brackets, we are going to get minus 3 plus 4 minus 12 plus 5. And if we simplify the answers, it's going to be minus 6. So we have to write here minus 6. On the second problem, it's about the knowledge of the knowing the properties of the determinants. So where we are given the P and Q matrices, which are 5 by 5 matrices, so 3 times is a determinant of the 2 P transpose to Q inverse. So knowing the properties of the matrices or the determinants of the matrices, we can write down this determinant as the 2 times as the I identity. Let me write as 5. It is going to be identity matrix, which is 5 by 5, times is the determinant of the P transpose times is the determinant of the Q inverse. So 3 times. So if you multiply the 2 to the identity, so all of the diagonal entries of that identity matrix is going to have 2, and we know that the determinant of the diagonal matrix is simply the multiplication of the diagonal entries. So it's going to be 2 times is a 2 5 times, or 2 in the power of 5. So determinant of the P transpose is the same as the determinant of the P, which is going to be 3, times is the determinant of the Q inverse is going to be the reciprocal of the determinant of the Q, which is going to be 1 over 2. So it's going to be 9 times 2 in the power of 4, which is going to be 9 times 16, which is 144. So in the problem number 3, we need to validate the values for the lambda and mu so that these two vectors are parallel. So please note that these two vectors are parallel if you can get one by just multiplying a constant. So when you can get one vector by just multiplying a constant to the second vector. So here obviously lambda is going to be 0 because this is 0 here. And if you notice that the second vector in the omega, so the numbers are just twice the numbers of the v, right? So that's why the mu is going to be twice smaller than the 4. It's going to be 2. So essentially, lambda is going to be 0 and mu is equal to the 2. And if you substitute this, the scaling coefficient k is going to be equal to the 2. So essentially, if you multiply v to the 2, we are going to get omega if lambda is equal to the 0 and mu is equal to the 2. So in a problem number 4, we need to multiply these two matrices. So let's multiply. So we're going to multiply this like a row by column. The first row to the first column. What we get is 1 times is a 1, 2 times is a 2, and 5 times is a 5, or minus 5 times is a minus 5. That's going to be 30. So now if you multiply the first row to the second column, what you get is minus 2 plus 0, which is 0. So that's going to be here. If you multiply the first row to the third column, what you get is 1 plus 4 minus 5, which is also 0. It's going to be 0. The second row to the first column, it's going to be minus 2 plus 0, which is 0. The second row to the second column, it's going to be 4 plus 1, which is 5. And if you multiply the second row to the last column, it's going to be minus 2 plus 0, which is also 0. The third row to the first column, it's going to be 1 plus 4 minus 5, which is also 0. So the third row to the second column is going to be minus 2 plus 0, which is 0. And the third row to the third column, it's going to be 1 plus 4 plus 1, which is going to be equal to the 6. So that's going to be the matrix. So in the problem number 5, we need to find the product of the eigenvalues of this matrix. So we know that the product of the 4 eigenvalues of this matrix is going to be equal to the determinant of this matrix. So we don't need to find all of the eigenvalues in order to find their products. And the determinant of this matrix is pretty easy to find because we see that the two rows, the first two rows of this matrix are linearly dependent. So essentially you can get one row by just multiplying the second to the constant. And we know by the property of the determinants, if the two rows are linearly dependent, then determinant is simply equal to the 0. So in the problem number 6, we need to find the eigenvalues of the A in a square. So if the matrix A is given like this. So there are two ways. Either we square the matrix A, then find the eigenvalues. Either we can find the eigenvalues of this matrix, lambda 1 and lambda 2. And the eigenvalues of the A in the square are going to be simply lambda 1 in the square and lambda 2 in the square. So we are going to use the properties of the eigenvalues. Essentially, the sum of the two eigenvalues of the matrix A is going to be equal to the trace of this matrix. The trace is the sum of the entries on the diagonal of this matrix. It's going to be 2. And the lambda 1 multiplied to the lambda 2 is going to be the determinant of this matrix, which is going to be 1 minus 9, which is going to be minus 8. Okay, so I think the two eigenvalues are going to be equal to 4 and minus 2, so that the sum is going to be equal to the 2, and the multiplication is equal to the minus 8. And the lambda 1 in the square is equal to the 16, and the lambda 2 in the square is going to be equal to the 4. They are going to be the eigenvalues of the A in the square. So it's going to be 16 and 4. So in this problem, we need to find the inverse of this matrix. So it looks like the elimination matrix. So where we have this 2, 1, it means that we need to add the 2 times the first row to the second row, right? So what we can do is, in order to revert the operation back, we can just like put the minus 2. So it's going to be okay, so let me explain you this operation. This operation means 2 times the row 1 plus the row 2. Okay, so you used to have row 1 and you obtained this one. So sorry, row 2. You used to have row 2 and you obtained this one. So what you have to do in order to get back the row 2 again. So in order to get back row 2 again from here, you need to subtract the row 1 times the 2. So 2 row 1 plus row 2. This is now our current state. If we subtract the 2 row 1, we are going to get exactly row 2, right? We will basically come back to the row 2. Okay, so that's why we have to put minus 2, 1, and 0. And this operation here, 1 over 2, means that the third row is going to be basically divided to the 2. So we used to have the third row. This 1 over 2 means that it's going to be row 3 times the 1 over 2. So what we have to do in order to get the row 3 again, we have to multiply this to the 2, right? So we have to multiply this to the 2 in order to get row 3. So 2 times the row 3 times, so 1 over 2 row 3, right? Will give us the row 3. So this is going to be the inverse of this matrix. So in order to understand this better, you need to look to the topics of the elimination and the permutation matrices. So in the problem number 8, we need to evaluate the dimensions of the following four spaces of the matrices. So we're given a matrix with the 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 columns and 9 rows. And the rank of this matrix is equal to the 6. Okay, so it means that 6 of the columns of this matrix are the independent. So the dimension of the column space is essentially about the number of the independent columns, right? So we know that 6, 1, 2, 3, 4, 5, 6, 6 of the columns, 6 columns are independent. And they are going to be the basis of the column space of the matrix. So that's going to be the 6 here. The same is going to be for the row space. So essentially, if you transpose this matrix, it's still 6 of the rows, or the 6 of the columns is going to be independent. So that's why the dimension of the column space is also going to be 6. Now, when we're talking about the null space is about the free columns, right? So if the six columns are independent, or they are going to be called the pivot columns, the rest are going to be the free columns. So how many? We're going to have 7 free columns. So, well, the number of the free columns define essentially the dimension of the null space. So it's going to be 7 here. And the dimension of the A transpose, if you transpose this matrix A, it's going to have 9 columns, 1, 2, 3, 4, 5, 6, 7, 8, 9 columns. And since the rank is equal to the 6 still, so this is going to be for the A transpose, this is for the A, 6 columns are going to be still independent. And in this case, how many columns are free? So there are going to be 3 columns which are going to be free. So that's why the dimension of the null space of the A transpose is going to be equal to the 3. So this is, we need to validate those numbers. Problem number 9, we need to validate the entry of the AB, which is located in the 3 and 2. So in order to do this, we don't need to multiply the whole matrix, all these 2 matrices. We're just enough to multiply the third row of the A to the second column of the B. And we have to multiply this again component-wise. It's going to be 2 times the 0 plus 2 times the minus 1 plus 1 times the 3 plus 0 times the 3 plus minus 3 times the minus 2 plus 1 times the minus 2. So let's open the brackets. It's going to be 0 minus 6 plus 3 plus 0 plus 6 minus 2. Right? So I hope that I'm doing everything correctly. Then the 6 and the 6 are going to be cancelled out, and this 3 with this minus 2 is going to be equal to 1, right? Okay, let me calculate this one more time. So it's going to be 2, oops, sorry, 0, 0 minus 2. Oh, it's minus 2 here, not minus 3. Okay, minus 2 plus 3 plus 0 plus 6 minus 2. Okay, so it's going to be 9 minus 4, which is going to be equal to the 5. So essentially, it's going to be 5. So sorry, here, that should be 2. So in the problem number 10, this is going to be the last problem of the first section. We need to find the elimination matrix, right? So in order to eliminate this 1, we have to multiply the first row to the minus 1 and add this to the second row. And this result should go to the second row, right? So that's why on the place of the second row, we have to put minus 1, 1, and 0. So essentially, this minus 1 is this minus 1. So this 1 is here. And this is going to be the result. So, and the rest is going to be zeros. So that's going to be the elimination matrix. So this is the first section. In the second section, we need to answer 5 true/false questions. So the let A transpose and its transpose is equal to the A, then A is a metric matrix, so which is a false statement in general, because any matrix will fulfill the statement, right? So in order to show that that statement is false, it is just enough to give a one counterexample. So for example, let's take 1, 0, sorry, we can take 1, 1, 0, 0. That's obviously not a symmetric matrix, right? So if you transpose this and then transpose this again, we obviously are going to get 1, 1, 0, 0, right? So the thing is that the statement that this works doesn't mean that the matrix is symmetric. So any matrix will work for that. So second statement is also false, because we know that the AB in the square is equal to the AB times the AB, right? Which is not A in a square times the B in a square. Okay, so a homogeneous system of linear equations is always solvable, it has always a solution, which is the true statement, right? So we know that a homogeneous system of linear equations, Ax is equal to the 0, is always the trivial solution, x is equal to the 0. Then if the matrix A is singular, so essentially if it has the 3 columns, then it might have the infinitely many solutions. So a square matrix is invertible if and only if 0 is not an eigenvalue. So we know that the matrix A is invertible if and only if the determinant of the matrix A is not equal to the 0, and if all of the and we know that the determinant of the matrix is equal to the multiplication of all of the eigenvalues if none of them is equal to the 0, then obviously it's not going to be equal to the 0. The multiplication is not equal to the 0, and consequently, the matrix A is invertible. So essentially, that's going to be the true statement as well. And the last statement, let R is the reduced row echelon form of the matrix A, then the column spaces of the A and R are the same, which is the false statement, right? So the easy example would be, let's say A is going to be equal to the 1, 1, 0. Oh, sorry, 1, 1, 1, 1. Then the column space of this matrix A is going to be the span of this column, right? 1 and 1. So essentially all of the vectors along this line, 1 and 1 line, and the row echelon form of this matrix is going to be equal to the 1, 1, 0, 0, right? So when we multiply the first row to the -1 and add this to the second, we will obtain this one. And the column space of the R is going to be the span of 1 and 0. So it's going to be all of the vectors along this vector. So essentially, they are not the same. So that's going to be the false. So now let's go to the last section where we need to solve the 2 problems. The first problem is about the SVD decomposition. We are given a matrix. So we just need to follow all of the instructions which are given here. In the firstly, we are going to multiply the A to the A transpose. It's going to be 1, 1, 0, 0, 1, 1. If you multiply the first row to the first column, it's going to be 2. The first row to the second column, it's going to be 1. The second row to the first column, it's going to be 1, then 2. So 2, 1, 1, 2. So you'll get 2 points for this part. And the second problem, we need to find the eigenvalues of the AA transpose. In order to do this, again, I'm going to use the property. So the sum should be equal to the trace, which is 4, and the multiplication should be equal to the determinant, which is 4, minus 1, which is 3. So obviously, I can get here that the first eigenvalue is 3, the second eigenvalue is equal to 1. Please note that whenever we find the eigenvalues of the AA transpose, we need to numerate them in descending order. So essentially, the greatest eigenvalue should be the first, the second greatest eigenvalue should be the second, and so on. While the singular values are just the square roots of the eigenvalues of these matrices. So it's going to be a square root of 3 and square root of 1, which is simply 1. So now we need to find the vectors U1 and U2, so which are going to be the eigenvectors of the AA transpose. So please note that here we have to use the eigenvalues of the AA transpose, not the singular values. So essentially, here we have to use 3 and 3, not the square root of 3, because square root of 3 are the singular values, not the eigenvalues of the AA transpose. So the AA transpose is 2, 1, 1, 2. And if I subtract this 3 from its diagonal entries, it's going to be minus 1, 1, 1, minus 1. So you see, so these two columns are really similar. So which operation will just make their linear combination to be equal to 0? So essentially, if you just sum them, right? So if you multiply the first column to the 1, the first column to the 1, and the second column to the 1, and if you sum them, we're going to get simply 0 and 0 here, right? So the U1 is the normalized version of this 1 and 1 vector. It's going to be 1 divided to the square root of t and 1 divided to the square root of t. And we're dividing this to the square root of t because the norm of the x1 is equal to the square root of t, which is 1 in the square plus 1 in the square, which is square root of t. So well, this vector is the unit vector. Okay, so it's important because when we put this vectors U1 and U2 as the columns of the matrix U, the U matrix should have the orthonormal columns. So the second one is going to be found in the same way. So it's going to be 2, 1, 1, 2. We have to subtract the matrix where the second eigenvalue, which is 1 times the identity, 1 and 1. If you subtract, it's going to be 1, 1, 1, 1. Again, I've got two columns, this column and this column. So which combination will just make it to be equal to the 0? So in this case, obviously minus 1 and 1, right? If you multiply the first column to the minus 1, the second column to the 1, and add, we're going to get 0 and 0. Now we are going to again normalize this. It's going to be minus 1 over square root of 2 and 1 divided to the square root of 2. So now we need to find a V1 and V2. So it's already given the hint that in order to get this, we have to multiply these two matrices. So let me see what was the A transpose. A transpose is 1, 1, 0. 1, 1, 0, 0, 1, 1. We have to multiply this to the U1. So please know that it doesn't matter to which vector you're going to multiply, to the 1, 1, or to this vector, because you're going to normalize this anyway. So I would just prefer this to write 1 and 1 here, because I will normalize this anyway in order to get the V1. So V1 is going to be the same. It doesn't matter which vector you use, x1. So essentially, x1 vector you're using, or the U1 vector you're using, you're going to get the same vector V1. So it's going to be 1, 2, and 1. So 1, 1 means that we just need to add these two columns of this matrix. And if you normalize this, so what is going to be the norm of this vector? The norm of this vector is going to be square root of 1 plus 4 plus 1, which is the square root of 6, right? You have to divide all of the entries to the square root of 6. It's going to be 1 divided to the square root of 6, 2 divided to the square root of 6, 1 divided to the square root of 6. So now we are going to multiply the A transpose 1, 1, 0, 0, 1, 1 to the second vector, which was like minus 1 and 1. It means that we need to subtract the first column from the second. It's going to be minus 1, 0, and 1. So the norm of this vector is square root of 2, so that's why it's going to be minus 1 divided to the square root of 2, 0, and 1 divided to the square root of 2. And the last part, we need to find the V vector, V3 vector, which is going to be orthonormal or orthogonal, sorry, to the V1 and V2. So the vector V3, which is going to be orthogonal to the V1 and V2, can be found by just multiplying the V1 to the V2. Okay, so let's multiply the V1 to the V2 as a vector product. So I'm going to put the I, J, and K. And here, instead of using this ugly vectors, V1 and V2, I'm just going to use these vectors. Because it doesn't matter, the goal now is to just get an orthogonal vector, V3, then we can always normalize this, right? So essentially, I'm just going to write this like, you have now two vectors, V1 and V2, and your goal is to find this V3 vector. It doesn't matter whether you use the different lengths as vectors of the V1 and V2. So if it is easier for you to do that, then just do this, because you just need to find the direction of the V3, because you're going to just normalize this anyway. You will make this unit vector anyway. I'm going to use these two vectors. It's going to be 1, 2, 1, minus 1, 0, 1. So the determinant of this matrix is going to be I times the determinant of the rest, which is going to be equal to the 2, right? So minus j times the determinant of the matrix, which is left, is going to be 1 plus 2. It's going to be 2 plus k times the determinant of the matrix. When we eliminate the third column, the first row and the third column, it's going to be 2. So the vector v3 is going to be 2 minus 2 and 2. And if you normalize this, so it's going to be v3 is going to be 1 divided to the square of 3 minus 1 divided to the square of 3 and 1 divided to the square of 3. Essentially, you've got this v vector, which is going to be long, right? So which is minus 2, and 2. And what I'm doing is I'm just getting the vector v3, which is in the same direction as this vector, but it's a unit vector. So 3 here, right? 3. Cool. So this is going to be all the 3 vectors v. And if you just put all of the 3 vectors into the matrix, we're going to get the SVD decomposition U sigma V transpose. U sigma V transpose. The last problem is about the QR decomposition of this matrix. Let's say we are given the M matrix. We need to find the QR decomposition of this matrix. So in order to do this, we need to get first of all, the Q1 and Q2 columns. In order to get them, first of all, we need to get the V1 and V2. So it's already given the formula. V1 is the first column of the M. So C1 of M means the first column of the M, which is going to be 1, 1, and 1. So V2 is the second column of the M, so which is 1, 2, 0. Not this V vector, right? The second column of the M, which is going to be equal to the 1, 2, 0, minus the second column of the M times the V1, which is going to be 1, 2, 0 times the 1, 1, 1, divided to the V1 transpose is the V1, which is 1, 1, 1 times the 1, 1, 1. And all of this is multiplied as a V1, which is 1, 1, 1. So that's going to be 1, 2, 0 minus. If you multiply this vector to this, it's going to be 3. This vector to this vector is also 3 times the 1, 1, 1. So 3 over 3 is going to be simply equal to the 1, right? If you subtract those two vectors, it's going to be equal to the 0, 1, and minus 1. So the Q1 and Q2 are simply the normalized versions of the V1 and V2. So the Q1 is going to be 1 divided to the square root of 3, 1 divided to the square root of 3, and 1 divided to the square root of 3. And the Q2 is going to be 0, 1 divided to the square root of 2, minus 1 divided to the square root of 2. Okay, so now in order to get the R matrix in the QR decomposition, we just need to multiply the Q transpose to the M. So the Q transpose is 1 divided to the square root of 3, 3, 3. 0, 1 divided to the square root of 2, minus 1 divided to the square root of 2, multiplied to the M matrix, which is 1, 1, 1, 1, 2, 0. 1, 1, 1, 1, 2, 0. So if you multiply the first row to the first column, it's going to be simply the sum of this square root of 3's. It's going to be equal to 3 divided to the square root of 3. The first row to the second column is also going to be equal to the 3 divided to the square root of 3. So the second row to the first column is going to be equal to the 0. The second row to the second column, it's going to be 0 times the 2 times the square root of 1 over square root of 2 plus 0. It's going to be 2 divided to the square root of 2. Or a simplified version is going to be square root of 3, square root of 3, 0, square root of 2. Okay, so now we need the Q and R matrices in order to solve the least square problem. So essentially mx is equal to the b. So here I'm just going to substitute the m with its QR decomposition. QRx is equal to the b. So you can get rid of the Q by just multiplying the Q transpose from both of the parts. Q transpose from here and here. And since Q is orthogonal matrix, this is going to be simply identity. So the Rx is equal to the Q transpose to the b. So let me first of all multiply the Q transpose to the B. So the Q transpose is 1 divided by the square root of 3, 3, 3, 0, 1 divided by the square root of 2, minus 1 divided by the square root of 2, times the B vector. So let's go and see what was the B vector. B vector is 1, 0, 1, 2. 0, 1, and 2. So the first row to the first column is going to give you square root of 3 simply, right? And the second row to the second column here is going to be 0, 1 divided to the square root of 2 minus 2 divided to the square root of 2. It's going to be 0, 1, 2, yeah, square root of 3 minus 1 divided to the square root of 2. Okay, so the R matrix is square root of 3, square root of 3, 0, square root of 2, times to the x1 and x2, this is going to be our x vector, is equal to the square root of 3 minus 1 divided to the square root of 2. So let's solve the second column, first of all, the second row, sorry. So the 2 square root of 2, square root of 2 times the xt is equal to the minus 1 divided to the square root of 2. So from here we obtained that xt is equal to the minus 1 over 2. So we have to substitute this to the first equation. The first equation is square root of 3 times the x1 plus square root of 3 times the x2 is equal to the square root of 3. So we can just divide everything to the square root of 3 and we'll obtain x1 plus x2 is equal to the 1. So now, since we know that x2 is equal to the minus 1 over 2, it's going to be x1 minus 1 over 2 is equal to the 1. We'll obtain that x1 is equal to the 3 over 2. So that's going to be the least square solution for this problem. This is the solution for all the problems on this final exam. Thank you very much. I hope that this was helpful.